So hi everyone, my name is Manu Sporny. I do a number of things, but one of the things I do is I'm a standards editor at the World Wide Web Consortium, and I'm part of the Verifiable Credentials Working Group at the World Wide Web Consortium. And one of the standards that we're working on right now is a digital signature family called data integrity, so verifiable credential data integrity. I'm also the founder of a company called Digital Bazaar that's been around for about 20 years. We do work with federal government, state government in the United States, as well as Canada, European Union, Asia Pacific region. A lot of our focus is on digital credentialing, specifically using verifiable credentials to deploy government-issued identity documents. So things like we work with U.S. Citizenship and Immigration Services in the United States. We work with DMVs, Department of Motor Vehicles in the United States, to issue digital driver's licenses, and things like employment authorization documents, permanent resident cards, citizenship certificates, naturalization certificates, all issued as verifiable credentials. And one of the things, as everyone knows, that you need to do with a verifiable credential is secure it. So we're going to be talking about the different ways of securing these verifiable credentials. And some of this does apply to more than just W3C verifiable credentials. As everyone knows, MDoc, MDL is also in play. There are new digital credential formats being proposed all the time. And so we can talk about all of those things and how this mechanism can apply. But for today, the key thing we're going to focus on is how to get different privacy qualities out of these verifiable credentials in a way that meets national and state standards, like cryptographic standards, like NIST standards, ETSI standards, things of that nature. Okay, so basically we're talking about digital credentials and how to secure them, simultaneously meeting national cryptography goals and privacy cryptography goals at the same time. I think we're just going to cover like what are the challenges specifically around cryptography and parallel signatures. We'll talk about the solution that is being standardized at the World Wide Web Consortium called Data Integrity. We'll go through how it works in a fair amount of detail. Happy to dive even deeper into the cryptography if people want. And then we can have a discussion after that. Okay, so let's talk about the security, privacy, and format challenges that we currently have with digital credentials of all types. So there are three competing challenges that we have today. One of them is a security challenge. So we needed a way to secure a verifiable credential that complies with government cryptography standards like NIST, ETSI, IEEE, ISO. Each one has slightly different requirements. It gets even more complicated when you get into like cryptography standards in the Asia Pacific region, things like SM2 and things of that nature. So we have a number of competing interests when it comes to cryptography formats across national governments. And one of the things we're trying to do with verifiable credentials is get a national body to issue a digital credential that is then consumable anywhere in the world. So there are requirements that each national body has. Sometimes they don't align at all. So we have a security challenge. The first thing is we need to make sure that these credentials are consumable anywhere in the world, but understanding that different national bodies have different cryptography requirements. The next thing is a privacy challenge. So we need to also make sure that we're protecting an individual's privacy when they use these digital credentials. So the traditional way of doing digital signatures is a full disclosure of the information that's signed. So if you do a digital signature over a PID, a personal ID document, or a driver's license or a employment authorization document, when you show the credential, every single field is shown. And that is not good from a privacy perspective in many use cases. There are newer selective disclosure mechanisms that are being proposed that allows the individual, the holder of the digital credential, to selectively disclose certain fields. However, because of the way the national standards work, even when you present even a selectively disclosed credential, like using SDJOT, it is a permanent tracking token. The digital signature acts as a permanent tracking token that can be tracked anywhere you use that, and which means that the individual can be correlated very easily from presentation to presentation. And finally, there's newer cryptography like anonymous signatures, BDS that does unlinkable signatures that are safer from a privacy perspective, but not recognized by national standards bodies and will probably not be recognized in the next couple of years. So we have this privacy challenge that we're also trying to do. We're trying to make sure that we can sign these things according to national body cryptography standards, but we also want to make sure that we provide options to verifiers and holders in the ecosystem to make sure that they can protect their privacy when they do things in the ecosystem. And finally, we have a format challenge. So it's easy to reissue a credential in every single different security format. However, that creates a tremendous amount of complexity in the ecosystem, meaning that a digital wallet now needs to support 4 or 5 or 6 different formats for each privacy thing you're trying to achieve. Wallets need to manage that. Issuing systems need to manage the idea that they have multiple digital credentials issued in parallel for the same PID or the same driver's license, for example. So all of these things were what went into trying to address the challenge. There are really 2 options for a solution here. The first option is effectively taking your payload, the verifiable credential or digital credential, and enveloping it in a certain format and then digitally signing that. So you basically take the payload and you encapsulate it in a higher level format and you stamp it, you digitally sign it. So these are examples of these types of formats are like VC-JOT, VC-HOSI, VC-COSI, SD-JOT, JWP. Each one of these is a different kind of enveloping format, and if you want to support different privacy characteristics, you have to keep reissuing you have to issue parallel multiple of these formats into a digital wallet. So the nice thing here is that it's simpler for security software implementers. So people that are actually implementing the digital signature portion of it, it's easier for them because all they do is they take the payload, they encapsulate it, and they shoot it out into the ecosystem. The problem, as I mentioned, is in issuer complexity. Like the issuer has to issue 4 or 5 different credentials for one credential. The protocols become more complex because you have to send many different credentials across. The wallets become more complex because they have to manage, they have to understand that this one format is actually linked to these other formats and it's actually the same credential. And so that's the challenge there. So it's easier to take off-the-shelf tooling, wrap it, and deploy it, but it creates complexity in the ecosystem. The other approach, and this is the parallel signatures approach, is that you take one payload and you attach a different proof to the same payload for every single security and privacy feature that you want. So what that means is that you will have one verifiable credential or one digital credential of some kind, and that credential will have different proofs on it, different digital signatures, and each digital signature will provide different capabilities to the holder of that credential. So what the nice thing here is that it doesn't obfuscate the data. You can process and store your verifiable credential as plain JSON. It's simpler to manage for most developers. So the developers that are doing the wallets and the issuing software and the verification software only need to deal with one payload, one digital file that has multiple proofs on it. This also means that you use the same security format for all these different features. So there's a nice ability to support everything in the ecosystem today, and you have future cases where if you find a new privacy protecting mechanism, a new security mechanism like a post-quantum signature, then you just add it to the end of the list of the proofs. So it's very easy to kind of upgrade what's already out there. I've mentioned that it's simpler for developers. However, there's a drawback. I mean, this is this is really a discussion about around where does the complexity get pushed. You either push the complexity down to the cryptography layer, or you push the complexity up to the application layer. The parallel signatures approach for the World Wide Web Consortium's data integrity approach pushes the complexity down to the cryptography layer, to the people that are writing cryptography libraries, which means it's much more complex for them to implement this. But at the same time, there are very few of those developers. They're highly trained at what they do. They can be audited. You know, you kind of push the complexity down to an easier to deal with developer population. Okay, so I kind of covered this a bit. This is, you know, technology is all about trade-offs. If you have if you have a certain set of features that you need to support in the ecosystem, the question is, where do you push the complexity? Usually you push the complexity down the stack or up the stack, depending on, you know, the use case. So effectively, that's what we're talking about here. You know, the securing formats, where are you pushing the complexity? Do you push it down to the securing format, or do you push it up to the rest of the ecosystem? Okay, so that's kind of the challenge that we had in front of us. This work started in 2015, so almost 8 years ago. That's the challenge that we had in front of us. And I'll go into kind of what the solution ended up being. But let me pause here for a second. Does anyone have any questions so far about the challenge? Okay, I'm not hearing any questions, so I'll keep going. Okay, so what's one way of solving this problem? There's a set of standards called W3C data integrity that supports this concept of proof sets. So a digital signature is a type of proof. You can also have other types of proofs like proof of work, proof of stake, proof of existence, things of that nature. So that's why we call them proofs and just not digital signatures. Digital signatures are just one type of proof. The W3C data integrity work, as I said, started around 2015. It's taken quite a long time to get it standardized because we wanted to make sure we got, you know, all parts of it right. And fundamentally, the technology allows you to attach multiple proofs to a single payload. So everything's, you know, encapsulated in one payload, where each proof gives you different cryptographic properties or different privacy properties. These specifications that I'm talking about are in the candidate recommendation stage at the World Wide Web Consortium. What that means is that's the final stage before ratification of the standard. We are expecting that these will be global standards this year. And, you know, the timeline for when they become global standards is dependent on continuous security review, implementations, deployments and experience, people reading over the algorithms, making sure we got them correctly. There's foundational work going on at the Internet Engineering Task Force that we're dependent on that needs to be finished before we finish. But the expectation is data integrity will be a global standard this year, probably late summer. And then the data integrity suites, most of them will become global standards around the same time, with BBS, specifically the unlinkable signature suite, trailing by a little bit. So that by the end of the year, more than likely. This is not a research project. It's not experimental. It's going to be a global standard this year. So how do parallel signatures work? Typically, the issuer starts with a credential that they want to issue to a holder. So this is a verifiable credential. Any kind of digital credential can be supported with this. But for right now, let's just say it's a verifiable credential. And then the issuer decides what type of privacy characteristics and security characteristics they want to enable on the credential. So for example, let's say I can speak to the federal governments that are doing this. Federal governments like the United States, federal government that want to be able to sign a verifiable credential with a standard NIST signature, full disclosure signature, because they're required to, in some cases, from a regulatory perspective, to sign it in that way. So that's one of the signatures that goes on there. But they also want to support selective disclosure. So they want to support selective disclosure using a NIST compliant security suite. So they put a second proof on it that allows NIST compliant selective disclosure. And then finally, they want to enable, because of privacy regulation in the United States, they want to enable unlinkable signatures on the same credential, because if they don't do that, then the credential becomes a tracking vector, a correlatable, highly correlatable tracking vector, because the signatures that are NIST approved, like ECDSA, they don't change per signature. So the issuer decides what characteristics they want the credential to have. National governments are incentivized, at least in the United States, to ensure that they support both selective disclosure and unlinkable disclosure. And they add all of those proofs and add all of those proofs to a single payload, and then hand that a verifiable credential over to the holder. The holder then keeps it in their digital wallet as a single, object. Now, when the holder goes to a verifier, the verifier can say, I accept, I want to see a digital credential like your citizenship certificate, but I allow you to present that in an unlinkable way, a selectively disclosed way, or a full disclosure. And they can give any one of those options to the holder. The holder will optimize for most of the digital wallets we're looking at right now, will optimize for the most privacy preserving mechanism. So if the verifier says, I accept BBS signatures and unlinkable signatures, then what the holder does, the holder software, the digital wallet, will take that verifiable credential and they will remove every proof that is not the unlinkable signature. They will derive a new signature, and then they will just send that with a single proof that's unlinkable over to the verifier. So that's kind of how parallel signatures work, the entire life cycle there. Let me stop there for half a second, see if there are any questions on kind of in general how that ecosystem is supposed to work. All right, so what does it actually look like? This is exactly what a credential looks like. I took this out of the verifiable credential playground a couple of days ago, I guess on the 2nd of March, that's when the signature is. And this is for a permanent resident card. This is one of the digital credentials that the US federal government is going to start issuing. And at the bottom, you can see that there are 5 proofs on it, 5 digital signatures. Each digital signature is a different type of digital signature. We'll go into the details of it, but this is what it looks like. You have a single payload, you have a proof, and you've got multiple digital signatures on there. And the issuer in this case has decided that they want 5 different security and privacy characteristics attached to the credential. So let's go through how it works. This is typically what the data integrity processing pipeline looks like. So you start on the left with a piece of data. I should highlight here that data integrity is not specific to verifiable credentials. It just so happens to be in the verifiable credential working group where a lot of the work is happening, because we wanted a concrete use case to focus on in the first iteration. But W3C data integrity can be applied to any JSON CBOR data structure. So it's a generalized signing technology. So the pipeline, let's say the issuer wanted to provide 3 different types of digital proofs, each with 3 different types of characteristics. They wanted to do a full disclosure one, that's the top in purple. So ECDSA is an elliptic curve digital signature algorithm. That is full disclosure. It's a full disclosure digital signature. It is compliant to NIST and ETSI standards, cryptography, standards. Typically, anyone in the world will take an ECDSA signed payload. The second one, the green pipeline, is ECDSA SD. This SD stands for selectively disclosed or selective disclosure. So the purple one at the top is full disclosure. The green one is selective disclosure. The selective disclosure one allows the issuer to say, I allow certain fields in this verifiable credential to be selectively disclosed. So the issuer here is taking the data and they're going to add a proof for selective disclosure. Finally, the one at the bottom, the red salmon colored pipeline at the bottom is BBS. So BBS is a type of signature mechanism that allows you to do selective disclosure, but it also allows you to do unlinkable disclosure. And what that means is that every time you present the BBS credential, a BBS secured verifiable credential, the digital signature will change in an effectively random way. It's verifiable still, but it's random, so that when a holder goes and presents a credential to one website and then they go to another website, it's untraceable. The verifiers could collude together and they would not know that it's the same individual. This is relatively new cryptography, and by new I mean it was invented in the early 2000s, so it's 20 years old, but it takes a long time for cryptography analysis to happen to the point that people feel safe using it. So BBS allows unlinkable signature. So we have three signature pipelines here: full disclosure, selectively disclosed with NIST and ETSI compatibility, and then BBS, which is not approved by ETSI or NIST for governmental use, but it is accepted by industry. So there are commercial organizations that will happily accept the BBS signature for privacy-preserving reasons. There's some really interesting regulatory reasons where you would prefer a BBS signature over a full disclosure or selective disclosure one. So what you do is you go through each one of these pipelines and you sign the data, and then you have data with the proof attached at the very end. So you have a single payload at the end that has three different signatures. Any questions on the processing pipeline? Hopefully that's fairly clear. All right, so let's look at what each one of these processing pipelines looks like. I'm going to just, I'm not going to go into excruciating detail on it because each pipeline could take an hour to kind of talk through. There are these details in the specification and other presentation decks. Let's look at the ECDSA processing pipeline. This is what the actual data looks like that's signed. So if you take a verifiable credential and you pass it through the ECDSA one, it converts it into these single line statements. So this is RDF dataset canonicalization that it does. You don't have to do RDF dataset canonicalization. You can do other types of canonicalization like JSON canonicalization scheme that doesn't do any kind of RDF or semantic anything. But we use RDF. I'll go into why a little later. Once you canonicalize it, it looks like this blob of data at the top left here. So this thing on the top left are the statements, and each statement is kind of read like a sentence, where you have a subject, which is the first value, the property associated with the subject, which is the second value, and then the value of the property, which is the third value here. So right here, you see that the C14N0 value, C14N stands for canonicalized or canonicalization, and 0 is this first kind of object you're describing. The description of the object is a Government of Utopia permanent resident card. So this is the description of the card itself, not the subject of the card, but what the card is. And you know, so on and so forth all the way down here. The subject of the credential is Jane Smith. You can see that kind of in the middle here. They've got a picture and the image, and then they have a legal permanent resident number and that kind of stuff. So this is the simplest pipeline. You basically take this data, you hash it, and you sign it, and you get an ECDSA signature, which is down here at the bottom. So you get effectively a 64-byte signature, which is a standard ECDSA signature, which is a 256-bit security level, and that's it. So you take the data, you hash it, you take the verifiable credential, you canonicalize it, you get this thing in the middle of the screen here, you hash that, you sign it, you get the ECDSA digital signature. So that's the first pipeline. The second pipeline for selective disclosure is slightly different. We still end up dealing with these statements, these kind of RDF statements. But when selective disclosure is used, there are a set of statements that are mandatory, and there are a set of statements that can be selectively disclosed. So why would you want to do that as an issuer? Let's say that you were dealing with a PID or a driver's license, and it's a long-lived credential, and you wanted to make sure that you provided some kind of revocation list. So you want the individual to be able to just disclose the driver's license number or just disclose their first name, but you also want to ensure that the status list, the revocation information is always has to be disclosed, right? So that's an example of a mandatory disclosure. Issuance date ranges are also things that organizations might require to be mandatorily disclosed. And then there are a bunch of selective disclosure selective disclosure statements, like this is an employee ID card, so the name of the corporation can be selectively disclosed, the division the employee is in can be selectively disclosed, the ID of the employee can be selectively disclosed, and so on and so forth. Their position within the organization. And then when you do the digital signature, this is the box at the bottom, you'll see that the digital signature itself is more complicated than just a standard ECDSA one, because you're allowing this to be selectively disclosed. So we have things like base signatures, there are ephemeral public keys that are used, there are HMAC keys that are used to anonymize some of the internal structure. So you don't accidentally reveal things, like if you were expressing information about yourself and you needed to disclose who one of your children are, you don't want to disclose that you have like 2 children or 4 children or 5 children, right? So there are set things that end up meaning like mathematical sets that you want to make sure you don't disclose, like how many entities are in the set. So that's what HMAC keys are for. They're mandatory disclosure fields where you basically say, you tell the verifier and the holder, these are the things that you always have to disclose. If you don't always disclose these things, the signature won't work. And then you have a selectively disclosed signature for every single selective statement that you want to disclose here. Those are this list of signatures here. And then, the total signature size for this, remember, like for ECDSA, it's just 64 bytes. For this, it's 640 bytes. Now, that's the payload that the holder gets. However, when they selectively disclose, if they do mandatory and selective disclosure, it's just 64 bytes per selectively disclosed item that they disclose. So the smallest disclosure size for ECDSA SD is about 128 bytes. And then you add 64 bytes for every piece of selective information that you want to disclose. Okay, so that's the selective disclosure pipeline. Any questions on that? I know, like, we're not going into any amount of detail on that, but does that make sense so far as to how we break apart the data and construct the signature?
Just one question.
Sure.
If you do it like that, are you not disclosing how many claims you have in the verifiable credential? So, for example, your example with the children, I could derive from the fact that you have like 20 signatures and every child is 3 signatures. I could derive that you still have four children, something like that. Did I get it? Did I get that right?
Yes, that's an excellent question. And we have a mitigation for that. So when the selectively disclosed information is provided to the verifier, they only see the signatures that are selectively disclosed to them. They have no idea how many selective disclosure signatures there are. They just see the one selective disclosure signature that was provided to them. So you can't, the verifier cannot see how many total statements were in the verifiable credential. They can only see the statements that were disclosed to them. They can also not see, if you have an array of values, they don't get to see how many items are in that array of values. So to them, it looks like you always have, if you're disclosing one child at a time, to them, it just looks like you only have one child.
Okay, that's clear now. Thank you.
Okay, yeah, that was an excellent question. It's an excellent question, and these are the questions that we've been grappling with for the past 8 years, right? It's very easy to accidentally over disclose things, And I will just say that some of the selective disclosure mechanisms in the field today that are being fielded do not have protections like that, or the protections that are there are not adequate. We can go into that later if folks want to hear about that. Anyway, so ECDSA-SD, that's in general how it works. Okay, so the BBS processing pipeline is very similar to the ECDSA-SD processing pipeline. So the good news here is that we were able to reuse a lot of the primitives that we had for the ECDSA-SD case in BBS as well. So you still take, the verifiable credential, you still break it into mandatory disclosure claims and selective disclosure claims. But when you go to digitally sign it, you do it in a different way because BBS is a different type of cryptography. It's a pairing-based cryptography mechanism. And you end up with slightly different characteristics. The key different characteristics with BBS, the main one that we really want there is that it's unlinkable, that you cannot use the signature to track the individual and correlate them from presentation to presentation. Every other mechanism out there has that flaw. I'm going to call it a flaw, right? I mean, I think we want to make sure that unlinkability is a privacy characteristic in these systems that we're building, and I don't think a digital credential solution is complete unless you have that at some level. So BBS allows us to have, a set of claims. You combine them into mandatory disclosure and selective disclosure schemes, just like ECDSA-SD, but now you sign with BBS. And when you do a BBS signature, the BBS signature is a fixed size. So it's it's smaller in many ways than the ECDSA-SD signature. You have a BBS header, which is used in the cryptography to make sure, certain things happen correctly. BBS has a public key that we include in the signature itself. We use an HMAC, again, to randomize information in sets so that people so they don't accidentally reveal. Again, you don't reveal how many children you have if you have an array in the data structure. You have a mandatory list of fields, but the total signature size for BBS, and this is a really interesting property of BBS, is small. It's 244 bytes, about 364 bytes when you base64 URL encode it. And with BBS, when you go to disclose it, the more you hide, the larger the signature. The less you hide, the smaller the signature. So BBS signatures tend to be fairly large if you are just selectively disclosing one or two pieces of information. And that's important because sometimes you have constrained environments, like you want to print out a verifiable credential on a piece of paper and a QR code. That's certainly possible to do, and we've gotten credentials down as small as 140 bytes, including revocation information, onto a piece of paper using verifiable credentials and data integrity. But a BBS signature would be, 2 kilobytes in size if you're hiding a lot of information, and that leads to a fairly large QR code on a piece of paper. So BBS signatures have two interesting properties. One of them is they're unlinkable. That's the main property that we want. And then the more you hide, the larger the signature. The less you hide, the more you selectively disclose, the smaller the signature. The less you selectively disclose, the larger the signature. Let me stop there for BBS. I don't know how familiar this group is with BBS or using it. Any questions on BBS or where that is or going?
How would it look like then with zero knowledge proofs?
Well, BBS is a zero knowledge proof, right? So I guess the question is, what do you mean by zero knowledge proof? Because a digital signature is a zero knowledge proof. It's a proof of,
let's say, predicates like over 18.
And so what do you mean by what would it look like?
The question, I would rephrase the question. Could we also use CL signatures in the same scheme? Instead of BBS proofs, add a CL proof, and then Kavnish-Lisinskaya has the zero knowledge proof capabilities, like we know them from OnonCreds. And then we basically could also use, well, maybe the format may not be the same, but at least the signature would be the same, and we would have the capability of a zero knowledge proof. Is that correct?
Yes. Yes, that is correct. In fact, we're working with the Canadian government on putting seal signatures into data integrity. They're actively working on a data integrity mechanism to express a seal signature. Yeah, yes, that's possible. Not only is it possible, but people are actively working on it, and the Canadian government is planning on deploying that probably starting next year, I think, is the current timeline. Did that answer your question?
And I guess the sorry, was the question answered, Michael?
Yes, it was.
Okay, yeah, thank you. So just maybe another question. So I guess the this is a kind of like an attachment, right? So you just sort of designate, okay, here's the signature, but it could also be a payload. So for example, to facilitate zero knowledge proofs, what one can do, just theoretically, right? We could use some of the, recent advancements in full homomorphic encryption, and just for example, more, like I have a certain number of children, and it's more than certain threshold, right? So I could encode it using the fully homomorphic encryption, and then the verifier could run the proof, right, on on the encrypted data to satisfy their need, right, for an attribute check. So we could actually embed that payload as kind of signature, right?
Yes, yeah, absolutely right. So that brings up an excellent point. So one of the design goals for the W3C data integrity work was to enable advanced and future cryptography schemes in parallel to the ones already accepted by national governments. One of the biggest problems that we have in cryptography right now is that it takes an enormously long time to get a government to accept a new type of cryptography. And one of the problems there is the cryptography, the enveloping formats that we have right now create this mechanism where it's all or nothing. You either use the envelope or you don't. And then there's this big race to like just focus on one envelope format, which doesn't have the privacy characteristics that we want. And so we were searching for a way to get governments comfortable with the fact that they would continue to issue credentials using cryptography that they know and trust and has been approved, like ECDSA, but also allow them to, in parallel, deploy fully FHE, ZKP, all these new types. In the theory, that it was a theory in 2015. Today, we have absolute confirmation from the U.S. federal government that this is okay. They have accepted that this is the way that they can deploy things. We have confirmation from NIST that they're comfortable with this approach. It doesn't mean that a federal government will accept the FHE signature or the ZKP signature, but what it allows them to do is it allows them to sign it, put it out into the market, and let commercial companies accept it, see how it goes. And if it's if the cryptography is broken or it's a disaster, you don't lose the original protection on the payload that the government put, ECDSA. It's just you lose that one FHE approach or ZKP approach. So we finally got these national governments to the point that they were comfortable doing parallel signatures. And that means that we can really accelerate the rate at which we can deploy new cryptography, privacy enhancing cryptography, fully homomorphic encryption, technology. So I think you brought up an excellent point. You asked, is it possible? Yes, absolutely. And in fact, it is a design goal to really push what we can do with cryptography at a much faster rate than what we've been able to do over the last 20 years. Did that answer your question?
Yeah. Thank you very much. Yeah.
Any other questions on the BBS portion? We're almost to the end here.
Yes, I have a question. Going
Yep.
back to ECDSA selective disclosure. So the reason why it is linkable, is it because a holder would always use the same signature or the same proof every time? Is that the reason?
Yes, yeah, exactly right. Yeah. In fact, that's the problem with, that's the problem with every national standard cryptography scheme today, is it is a permanent tracking cookie. When you disclose it to a website, you are giving them a tracking token, and they will use it. We know sites do this today, right? I mean, there are data brokers whose job it is to track you as you go across the web, and they will use anything that they can to track you. Browser fingerprinting. It's really nice if you just give them a tracking token, a tracking cookie, and a signature is that. So ECDSA is that. EDDSA is that. SDJOT is that. ECDSA SD is that. All of these, because the signatures don't change, are tracking tokens. And so one of the things, I'll try to be polite, one of the things that's confusing me is why national governments are saying that they're supportive of privacy regulation, but they're not pushing ZKP and anonymous signatures and things like BBS, because that's the only thing that actually allows someone to disclose these things in a way that doesn't result in a tracking cookie. I realize that some of the answer is like, oh no, only qualified parties are going to be able to ask for this information. But again, it's not a very good response there. So yes, that is the reason, Pascal. The digital signature, it's 64 bytes of cryptographically unique information. And if you present that at site A and site B, both sites get the same information and therefore can correlate you based on that. Did that answer your question, Pascal?
Yes, thank you very much. But I have an additional question, and selective signature. So when we go a slide further, the signature itself, is this just an addition of a subset of proofs? Is this a combination, or does this work in another way?
So for selective disclosure, was the question like for selective disclosure, how does it work?
Yes.
Okay, so see these selective, I went to the slide. So you have a base signature that is a 64-byte signature for all the mandatory fields. So we take all the mandatory fields, we hash them, and we sign them. That's the base signature. And then each selectively disclosed claim, each line here under selectively disclosed claims, we hash each line, and each line gets a digital signature, a 64-byte digital signature. So every line has a different signature. So you have the base signature, which covers the mandatory claims. You can have as many of those as you want. And then for each selectively disclosed claim, you have a different signature for ECDSA. Did that answer your question?
Yes, thank you very much.
Okay, so let's see, I'm gonna keep going, not much more here. So fundamentally, we went through all the processing pipelines, and what we get at the end here is something that looks like this. This is the final secured verifiable credential. It's one payload, and each pipeline above is basically reduced down to one signature in the set of proofs. So we have the ECDSA proof here, which is a full disclosure signature. We have the ECDSA proof here, which is a selectively disclosable signature, or set of selectively disclosable signatures. And then we have the BBS proof, which is an unlinkable disclosure proof. I shared the slide deck with many of the people on the call. You can click on these links here to see exactly, what this information looks like. So, this is the full, these are what the full proofs look like, and the proof values down here at the bottom. So if you wanted to go and really take a look at it, that's what it looks like. So that's it. So the other thing. Oh, go ahead, please.
Yeah, just a question. So excellent presentation so far. Really, well explained, even for novices, or not novices, but non-technical people like me. Just thinking about the implementation complexity of if a country would choose to go with BBS signatures and ensure unlinkability, what would it be in today's world from an implementation complexity and also from a usability perspective? Would that be a feasible approach actually to go, or is the BBS Plus scheme too complex to roll out to a very diverse set of holders?
That's an
and
excellent
verifiers?
question. I'm going to give you a slightly nuanced answer. So I'd love to say yes, but I don't think I can do that just yet. So you can try this stuff out today in the verifiable credential playground. So it is implemented, it is deployed. There's digital wallets that support it. There's issuing software, there's verification software, there's holder software that can do the selective disclosure. So it is doable and implementable and deployable today. There are the screens for selective disclosed BBS are not that complex, but here's, I have to caveat this, right? So the standard isn't done yet. That we have to ratify the standard at the Internet Engineering Task Force, which is expected this year, and we have to finish the standard at the World Wide Web Consortium, expected this year. Once those are done, there are not many software implementations for the BBS primitive. So there's one in Rust, there's one in C, which basically uses the Rust one. There are no Java implementations, but that can be solved with like, a $25,000, 25,000 to 50,000 euro could just make that, create it, right? And then the higher level libraries aren't that difficult either. So a single developer, one developer, can probably put the entire BBS stack together in a new language in about 3 months. That's how much development effort it would take. Working it into an existing wallet, like I saw the UD wallet open source release was just made recently, integrating it into a wallet like that would take about a single developer 2 to 3 months. And a lot of that is UI work, not cryptography work. So those are the timelines that we're dealing with. It's doable. I think anyone deploying this needs to take a dual approach, meaning use your nationally supported cryptography as a base layer, and then add the BBS stuff in on a different timeline. And I think realistically, BBS could go into production usage next year. You could definitely do pilots with it this year if you had the technical expertise on your team. Did that answer your question, Daniel?
Yeah, it did. And the acceptance in the ecosystem or the adaptability in the ecosystem, I think you mentioned earlier that corporations, businesses are typically willing to adapt higher privacy preserving and unlinkable kind of schemes. But we have a green field here in Switzerland, if you wish so. What would be your recommendation when you start on a green field? Because I'm not sure whether we have any hard dependency on NIST or ETSI at this point in time. And guys, correct me if I'm wrong, what is the national cryptography standard for EID and for level of assurance high type of use cases? I don't think there is any at this point in time.
There is. I mean, no, there is. Like for the UD stuff, the minimum.
We're not part of the European Union. That's my point.
Okay, no, that's a good point. So let me try and that is an excellent point. I'm saying if you want the credentials consumed outside of Switzerland, you would have to at least issue potentially using cryptography that the other EU members, EU member states would accept. So I think you have to issue using ECDSA full disclosure. I don't think that there's a way around that, or ECDSA SD selective disclosure. But to be precise, you will need to use elliptic curve cryptography. ECDSA is I think the bare minimum and what's going to be deployed. But on top of that, within Switzerland, and potentially outside Switzerland as well, you could just use BBS, right? And say that the default mode of operation in Switzerland is BBS or some kind of ZKP and on-creds, seal signatures whatever you wanted to use, and say when you go outside of the EU, you have to use this. The only one they will accept is this other one. I also think that you could probably drive the discussion if Switzerland decides that they're going to be doing some kind of ZKP scheme by default. That will change the entire UD discussion in the EU. I think. Agree. And you will have, I would imagine that you would have support from the U.S. federal government as well in that. I'm not speaking. Clearly, I'm not speaking for the U.S. federal government, but we work very closely with them, and they are looking for allies to talk about unlinkability being a requirement for citizens. Yes. So yeah, I agree with you completely. That, but I would imagine that if you wanted to hedge your bets, you'd have to do some kind of full disclosure scheme like ECDSA, and then you could do BBS CL signatures, something like that.
Yeah, we have a meeting coming up with Anil as well, I think so.
Excellent. Yeah. Good. Please bring it up. He will be supportive, I would imagine.
Yeah, so maybe just an additional sort of just question, and maybe just thinking out loud in terms of BBS signatures, right? So yeah, I've just checked. It looks like finally there is progress in IATF standardization. There was a updated draft at the end of December, and for a while it was actually very, very slow. So that's an encouraging sign. So that was my first question. Do you think that the standardization effort is proceeding there? And the second question, right, is, well, given the fact that BBS signatures are based on pay rate curves, and this is susceptible to potential quantum attacks, how acceptable is this, given the fact that for a lot of applications, especially around some sort of government, sensitive type of applications, the gather now or collect now, decrypt later type of attacks will be possible, right? So given the fact that, yeah, I mean, you can then restore the public keys and do all kinds of things, maybe even, forge the signatures and stuff like that. So, so these two things, the standardization, and is actually a good idea now to invest into new cryptography that is susceptible to quantum attacks?
Yeah, that's an excellent question, and that's another kind of nuanced. It needs a nuanced answer. So I think the NIST, at least in the U.S. federal government, has said that they will not be investing into any new selective disclosure mechanism that is not post-quantum resistant. BBS is not post-quantum resistant, just to be very clear there, right? So, but we don't know what that new thing is. It's it's magic right now, right? It doesn't necessarily. There are a lot of good technologies that are post-quantum, but the signature sizes, as everyone knows, are massive and gigantic and cannot be sent, over some channels. So there will be a data integrity suite that is post-quantum safe, that is selectively disclosable post-quantum safe. But there is no answer right now for unlinkable post-quantum safe. There are mechanisms that people are working on right now. And the nice thing about this parallel signatures approach is the second we feel like we've got something workable, we can roll out a new data integrity suite for it. So we at the W3C, the group is going to go in after the standards are done. We're going to go into a maintenance setting, which is we don't shut the working group down. The working group continues to work and operate, and we will, when those new mechanisms are available, rev new data integrity suites to be additive to that. So let's go back to BBS. The timeline for BBS at IETF is standardized. It's going through cryptography review right now, which is the last stage before it goes to final ratification. The world, that's at IETF. So it's already kind of in the last stages at IETF. You're right, it wasn't really moving that much for a number of years, and more recently we've been really pushing on it. At the World Wide Web Consortium, the World Wide Web Consortium has a new security area and a new security lead. Whose first job at W3C is to look at data integrity, BBS, signatures, that nature, and pull in academics to look at everything from the base cryptography on up all the way up the stack. That work is being done right now this year. So when will BBS be a final IETF RFC? This year, maybe as late as early next year, but it's on track for that. And effort is being put into it. Post quantum, can't say, but here's the thing. Don't confuse the digital signature with moving this stuff around. The gather, the collect and decrypt is about gathering data as it's flying across the wire. And Google and Cloudflare are already deploying chem solutions, post-quantum chem solutions, key encapsulation mechanisms to protect this information. So the transport matters. If the transport is protected using post-quantum cryptography, and that is being rolled out at a much faster pace, then the signatures within the channel don't really matter all that much. They still matter, but you've got this, hybrid post-quantum channel that's moving the data back and forth. That's providing protection. So this is, Kyber 765 plus X25519. They're X-Wing. They're all kinds of new channel encryption mechanisms that can be used to move these non-post-quantum safe signatures for the next couple of years. The timeline that we have to move onto post-quantum is 2035 in the US, which means that we really need to start now, and we have to get pilots up and running in the next 5 years so that we're ready to move over. But the data integrity mechanism, because of the way it works, because they're parallel signatures, all we do is just add another signature to the set of signatures to get post-quantum security on it. Did that answer your question?
Yeah, I think it's good. I also have an intuition that that the quantum attack on signatures is not as disastrous as in the encryption algorithms themselves, right? But still, right? Something to. It's good to hear that the common sense is like, maybe we can already sort of benefit from the crypto that exists, and drive some more privacy-friendly mechanisms. So yeah, but this is something that we need to be able to answer confidently, right?
Yeah. Here's the worst case solution is we can do hash-based signatures on verifiable credentials. We already know how to do it. We know that we can roll out a data integrity protection mechanism. It does not have to use any of the new post-quantum digital signature schemes. And we know that a quantum computer can't break it. So I don't think anyone should be panicking about us not having a solution. There is a solution. And if we needed to, we could rev a data integrity. Let's say that someone announces a quantum computer tomorrow that's capable of breaking cryptography. We could rev and deploy a new data integrity method that uses a hash-based signature within 3 months and have that deployed. Right.
Yeah, actually, since we're talking about that, so the reason I'm asking about FHE is there's been a recent advancement, relatively recent advancement here in Europe. There's a company called Zama, and they built a very interesting, FHE technology around learning with errors, which is quantum resistant, right? Yeah. So that might be very interesting, path to explore.
Yeah. And again, what we really tried to do with the parallel signature standard is to enable massive parallelization of experimenting with new cryptography while systems are in production. So you can deploy a verifiable credential in production today with an ECDSA signature, and you can add an FHE if for whatever reason a country in Europe just wanted to experiment with FHE, they would be able to do that in parallel with in a pilot setting or a production setting today. Pascal, I think you were next.
Yes, I have a question. So comparing these 3 different cryptographies, I understand that for ECDSA it is allowed, or it is okay to use hardware secure modules or secure enclaves, so that you can use your private keys with hardware bound proofs. However, on BBS, I understand this is not possible. And So my question here, how does this impact your parallel signatures, if it does in any way?
Yeah, that's an excellent question. It is possible. So, for example, our company has a capability for an HSM that is capable of doing BBS. There are other companies that are working on this. It is possible. You know, the demand's not there yet. I mean, you know, if someone starts doing digital signatures and they need an HSM that does BBS, there are a number of HSMs that could deliver that feature today. It's just there needs to be the demand there. So we know it's possible and it can be done. There are not many of those HSMs in the world, but at the same time, remember that even the NIST standards around in the US we have something called FIPS, the Federal Information Processing Standard, and that is how cryptographic modules are verified. Both the algorithms and the modules themselves are verified. There are very few use cases that actually require an HSM in operation. Military is typically where you, like, if you have an F-35 fighter jet, that is where you need, you know, an HSM. It turns out that if you look at things like government identity, those don't require an HSM. It requires a secure data center. It requires secure software operating in a secure data center. Ideally, you're using an HSM. But if you look at many governments around the world, they're not actually operating HSMs to do digital signatures around certain types of identity documents. So don't presume that an HSM is required for governmental identity, unless it very clearly says in your government standards that it's required. But that's certainly not the case in the United States. However, it is a good idea to use an HSM if you have the capability. And again, BBS, I don't think many people know this. BBS is already in hardware, like Intel ZPID thing. I mean, that ships. Every Intel processor that supports EPID, which the vast majority of them do, already use a pairing-based crypto. That's been true for nine years now. So it's not like this stuff doesn't exist in hardware and hasn't been deployed. It's just most people don't know about its existence.
Okay, I didn't know.
Did that answer your question?
But
yes, thank you
maybe
very
a
much.
follow-up one. But that would mean that you issue to cloud wallets, right? If you are using an HSM, correct? So if you need a secure element, need to use a secure element on an iPhone or an Android phone, that is a different beast, right?
It's an excellent question. Not necessarily is, I think, the answer. So remember, a BBS signature is generated by the issuer who gives the holder the entire payload, and the holder uses that payload to derive new signatures. So you can have an HSM that runs BBS on the issuer side. So the issuer says, I'm using an HSM, I'm creating a signature, I'm giving this to the holder. So that initial signature, BBS signature, is HSM secured. Once it goes out there to the holder doesn't necessarily need to use an HSM to derive a new signature. Now it's completely up to the use case. Like if for whatever reason, I can't think of a good reason why anyone would mandate that the derived signature has to be generated in an HSM, because that would mean that you would have to take the entire BBS credential and put it into an HSM and never extract it from the HSM and then derive subsignatures from it. I can't think of a good use case, a good reason to have kind of that requirement or that mandate. So all that to say, I don't think you have to use cloud wallets. I do think that cloud wallets are an excellent idea, and that is something, I think that's another mistake that's being made in the ecosystem, is presuming that there's going to be only a native app wallet that's bound to a mobile device. I don't think that's a very good design. So all that to say, we are not going to see BBS support in hardware on a phone anytime soon, I don't think. If we do, great, it's usable, but I wouldn't count on seeing it there. However, I don't think you need it for BBS. It's just, I don't think it's necessary. if you have the original signature, done in HSM. This of course comes down to like binding, hardware binding. If you need to prove hardware binding, there's no way to. You have to have hardware on the phone to do that, or as you said, or use a cloud HSM. So it is possible to have an issuer issue a BBS signature using a cloud-based HSM and have the holder use a cloud-based HSM to do the derivation and presentation. That feels like an incredibly high security use case to me, but it is, it is possible using a cloud wallet. I agree with that.
Yeah, follow-up question on this one as well, which would mean that would you be able to actually present in an offline mode using a derived BBS,
with an HSM or without an HSM? Without an HSM.
Both cases.
With an HSM, if it was on the phone, yes, but that's not going to happen anytime soon. So I would say no. You can't do offline presentation if you mandate an HSM on the phone. However, you can do offline presentation if you do not mandate an HSM on the phone. Did that answer your question?
Yes, thanks.
Now, I may expose myself as having no clue on how BBS actually works, but when you say derive signature, doesn't that involve some cryptographic material that actually is kind of bound to my person or to my device that I only have access to and nobody else, so that I'm the only one that can use it?
Yes, so excellent question. Another nuanced response, right? So the signature itself is all you need to derive the signature. So when the issuer gives you, Michael, the BBS credential with the BBS proof on it, that proof is the only thing that you need to derive the derived signature. So by having the signature, so that's important information. You don't share that with anyone else, because if you share it with somebody else, they can derive signatures too, right, and be unlinkable doing it. So what I'm doing is I'm describing the basic BBS signature scheme. There are extensions to BBS that do let you bind it to a device, so you have to have a hardware device or a certain protected cryptographic material, so that even if you share that signature, somebody else can't derive the signature with just the credential itself. So there are pseudonyms, there's issuer pseudonym binding, holder pseudonym binding, and I'm forgetting the third, blind signatures, an extra blind signature, mechanism in BBS. So there are mechanisms to do what you're saying, and they are in the specification, and they have, different benefits and drawbacks. So one of the dangers with BBS, the pure version of BBS, is that if somebody steals your credential or you share it, then you have multiple people in the ecosystem that can derive signatures, and you can't tell the difference between them. We published a paper about this probably about 7 years ago about, what if Alice was evil? What if you share your credential? What if you put it on the Pirate Bay for digital credentials? People can derive. So you have to have some way of binding the credential so that the verifier knows that that you're not doing that. And we can do even stronger binding to a physical device if we want to. Both the issuer can do that binding and the holder can do the binding themselves before they present it. So I don't know did that answer your question? There's a big it depends there. It depends on what types of BBS features you use.
Yes, I think it really answered my question, and I know not to use basic BBS for football tickets or movie theater tickets or something like that, right?
Yeah, but for age verification, it's a good idea, right?
Yep.
In any case, we have mitigations against this in the specification. We can get into depth about that later. And that was a very good question. I mean, that's one of the key things to be careful about with BBS. It's not magic. It's there are benefits and drawbacks. Any other questions on W3C data integrity or?
Yeah, so maybe the ability to add additional signatures is kind of cryptographic agility method, right? And as we know, cryptographic agility is a good thing, but sometimes can be abused, right? If either implemented incorrectly or people are not following, the protocol. We know that with JOTS, that's a famous example where people sort of wrote a bunch of libraries or just used libraries incorrectly. How much consideration has there been in terms of, understanding the implications of adding something like that?
Yeah, it's an excellent question. I don't think that there's been enough. Well, sorry. Let me go back to your statement about cryptographic agility. We have a definition for cryptographic agility and cryptographic layering. These are two, again, nuanced differences. Cryptographic agility is the ability to switch out your cryptography rapidly when you have two systems communicating on a fairly regular basis. When people say cryptographic agility, they usually talk about like SSL, being able to switch out the cryptography if a compromise is found in one of the core primitives, right? Parallel signatures is cryptographic layering. It's not cryptographic agility. Cryptographic layering is about adding multiple layers of cryptography so that if one of them is broken, the rest of the layers still protect the payload. Cryptographic agility has to do with you only have one layer and the layer gets broken. Can you quickly put a new layer in to protect it? So think of it as layers of armor on the original payload. Cryptographic layering and parallel signatures add multiple layers of armor on the payload, whereas cryptographic only has one layer of armor, but it allows you to rapidly switch the armor out. All that to say, there's slightly different concepts. Did that make sense? But I didn't answer your question. Could you please repeat?
But as you said, the difference is slight, right? So therefore, and again, I haven't spent a lot of time trying to think about this, but generally intuition is, hey, if there is flexibility in using cryptography, right? Let's put it this way, right? Which includes both agility and layering. The chances are that it's possible to abuse it, right? Not because it's poorly designed, but we all know that cryptography depends on assumptions. Like certain cryptography requires you to use, secure initialization vectors, right? And nonces and so on and so forth, right? And if you're not doing that, you are creating vulnerability, right? It's just a property of a mechanism that you use, right? And it stands to reason, right, to assume that if we're adding this flexibility, right, then it also demands certain types of assumption that people need to be aware of, and if they don't follow that, then a certain type of vulnerabilities will appear or might be discovered later. So the question was, how much thinking was there spent on kind of thinking about the implications of adding this flexibility? Let's put it this way,
Yeah,
right? Or layering.
Yeah, that's an excellent question. So there are two parts to that we have been thinking about for the past eight plus years. One of them is to reduce agility, not increase it, because when you have a lot of agility, you allow the attacker a lot of different entry points to attack. And so the data integrity cryptography suites make very specific choices on the types of cryptography that are used. So for example, the ECDSA crypto suite only supports P256 and 384, and that's it. Nothing else, because that's what has stood the test of time, will be okay until the year 2035. We tell people that they should not use the version of ECDSA that requires careful selection of nonces. So we tell people to use deterministic signatures because people have gotten the other version wrong. So we tell people not to do that. So data integrity, unlike a lot of the JWT, JWP, JW, SD-JOT stuff, very much says this is the version that you should use. So that reduces the attack surface. Now, we have multiple parallel proofs, and you're right there. We are allowing flexibility there, and that is an attack vector. So, for example, all the ways that things can go wrong. If you're using a BBS signature, what happens if you have a sloppy implementation and they just forward the original BBS signature to the verifier without deriving it? They've just compromised their credential, right? So there are examples like that where the wallets have to strip all of the proofs off that they don't understand. If they just blindly forward the entire payload to the verifier, and it's got a BBS signature in it, and it's not bound to a hardware device, they just lost their credential, and it could be used to. So there are examples like that where we know that that's a problem. We know that there's going to be some sloppy implementation out there that does that, even though we've told them in many different places in the specification don't do it, even though we have test suites that, you know, make sure that they don't do that. The only way I think to address things like that, like developers making mistakes, is to remove all the dangerous options. Like, for example, we don't support RSA at all at this point. It's just it's too hard to implement correctly. You know, ECDSA, EDDSA have better, you know, smaller parameter sets. And for those reasons, when we create these data integrity crypto suites, we are extremely limited in what the developer can pick, because developers that are non-cryptographers have demonstrated over the past 20 years that if you give them a dangerous option, they will accidentally select it at some point and deploy it into production and have a giant vulnerability, right? So
depending on what people say on what's it called, the developer side, the Stack Overflow or something. Yeah. On the forums, right, where people pick stuff on the forums. So anyway,
it's awful. And so we've been very conscious to do not allow developers to. One, the ideal is don't let them pick anything. Just do the most secure option that the entire cryptography community has agreement on. Don't create data formats that allow you to randomly select a whole bunch of different options and put them together. That was a really bad design decision. I think that the Jose community made, the ITF, you know, JWT community made, and has led to massive vulnerabilities. I mean, like the ability to say the algorithm, the encryption algorithm or the signature algorithm is none. It's not protected. That has led to, you know, countless, you know, security vulnerabilities. So all that to say, you know, we've learned from many of the mistakes that have been made before, and we try to be very specific about the type of cryptography to use, remove the ability for the developer to select dangerous options, and still ensure the ability to rapidly switch or create, you know, parallel signatures and create layers of armor around the payload.
Right, but it does sound like you know, but I guess it's a general problem, right? So it's the danger then, you know, when developers develop the wallets, they basically need to be aware what best practices are and understand cryptography anyway, right? Because what you're saying is, hey, the payload format is solid, right? It is well constructed, as much as we know. Obviously, yeah, there might be something discovered later, but it's well constructed so to prevent mistakes. However, you know, it does carry multiple signatures, and each of those signatures might come with its own, you know, security assumptions that people need to be aware of and act accordingly, such as not copying, you know, underwrite BBS plus signatures, for example, right? So, but that's a general issue. So basically, it's a question of how much can we trust the wallet developers to do the right thing, which basically means that, you know, if we want to build an HLO program and allow people to develop wallets, we need to be able to certify those wallets just to make sure that people are doing the right thing technically, not to create accidentally, you know, security flaws, right?
Yes, yeah, absolutely. Which is why we have test suites and conformance suites, and you're right, certification, especially when you're dealing with something like BBS, certification is vital. You have to make sure that that wallet isn't accidentally just forwarding the original, you know, credential over. I see Daniel has his hand up.
Yeah, just I mean, brings me to the point of asking what kind of recommendations would you put around as governance around the aspects of enabling parallel signatures for an ecosystem?
The minimum is have them demonstrate that they actually passed the test suites. What we are seeing in the market is a number of vendors just flat out lying about conformance with these standards. They're going to nation states, they're saying they're conformant. We know absolutely they are not. Luckily, the these governments are, communicating with the working groups and trying to find out. But there have to be test suites. There have to be conformance test suites that these developers are running against. They have to prove that, especially when it comes to the cryptography, they have to prove that they're actually implementing, per the standard in a secure way. On top of that, I think there's work that hasn't been done yet around, compliance and wallet auditing and things of that nature. I think the good news here, though, is that there's not a lot to get wrong. We have eliminated an enormous number of the choices, and so I don't think a compliance mechanism or an analysis really has to take long or cost a lot of money, but it is necessary. So the minimum necessary thing is demonstrate that you are compliant with the existing test suites. And as the ecosystem matures, I think we have to all invest in more test suites, more conformance test suites, more integration test suites. That's one of the whole reasons that the verifiable credential playground is out there, so that organizations, issuers, holders, and verifiers and digital wallets can test against themselves to see what problems there are. I mean, we are uncovering a large number of interoperability issues where developers thought that they had implemented things correctly, and when they actually try to connect up with another vendor, it turns out that there's some minor thing that's off, right? That reveals a bug in one platform or the other. Did that help, Daniel?
Very much, thank you. Maybe just one additional one. When you look at implementing countries, do these countries typically think about kind of establishing competency centers around these topics that are linked to W3C and some of the working groups? How do countries handle this knowledge gap?
Yeah, I think that's an excellent question. Right now, they are not. Right now, in some cases, well, I mean, we can look at the programs. I think, the UD wallet and the pilot programs are excellent. I think there needs to be a lot of transparency around how that goes. The U.S. federal government, is funding companies specifically to demonstrate interoperability and demonstrate integration and working with the standards bodies. But there are a number of initiatives now that are being driven by the vendors in ways that I think are unhealthy. I hate to say this, but I think there are some things happening in the EU around the UD wallet initiative that are largely vendor driven and not, government driven. So I think it's vital that governments have an independent view into the work that's happening. I think one of the ways of doing that is participating in the standards bodies to understand what the specification says and then what vendors, are saying. So I think that the governments are, deferring a bit too much to the vendors to pick the path forward rather than getting a full, deep understanding about what the choices are and then making separate kind of decision processes along with the vendors. I mean, it's very important to include the vendors in the process. They have a deep amount of expertise, but at the same time, of course, vendors also have commercial interests. So the government needs to have an independent opinion, in these matters.
And just in my head, what I foresee, at least for the future, is that public-private partnerships in these aspects, taking care of these aspects, are absolutely vital for these ecosystems to remain trusted and remain operational in an integral way.
Absolutely, I completely agree. Okay, so I think we're at the end of time. I don't know if I don't know how long these meetings go for, but I really appreciate all the wonderful questions and great discussion. This has been fantastic. If there's anything I can do, please reach out. Happy to answer anything over email. We're in the World Wide Web Consortium Verifiable Credentials Working Group. You don't have to be a member to participate in the discussion. The GitHub for this, all the specifications are open. The mailing lists are open. If you have a question or concern, just send an email or raise a GitHub issue. That's the way you can influence the global standards. Okay, with
Super.
that,
And
Thank you
Manu,
very much. Yes.
Manu, just one thing.
Yeah.
There is going to be a conference here in Switzerland that is going to run around some of the most important interoperability questions between the EU, but also UK, Switzerland. There might be participation of Sweden and so forth. It's running from the 18th till the 20th of June. So if you have a chance to come over, I think Anil also will be here. Some of the key people will join this conference. Have joined last year. It has been I think a great way to keep the conversation going.
Great. Thank you very much. It was really an excellent presentation.
Great.
Thanks for making it possible,
Thank
Manu.
you very much. Really appreciate the time. Of course. Anytime.
Thank you so much.
Take care.
Thank you.
Thank you.